Hello and welcome to Physics at the Coopers Company in Coburn School. My name's Mr. Bain. So our A-level physics course here at Coopers is OCR-A Physics, and you can see the code H556 here. The physics department is 4 members of staff. We have Mr. Diamond and myself, Mr. Bain, as joint heads of physics. And then we have Ms. Sosu and Dr. Crucius as other physics teachers. The course structure is made up of 6 modules. There's 10 lessons a fortnight, and there'll be 2 teachers per group. And we have a curriculum map which will be attached to this PowerPoint on the school website where you view this video, and that will show you all the different topics and assessments and the order that they're in. Just quickly though, the modules that we are teaching, there's 6 on the course: practical skills in physics and foundations of physics, and then we have forces and motion, electrons, waves, photons, Newtonian world and astrophysics, and then particles and medical physics. So we cover a wide range of topics in physics, lots of different areas from traditional mechanics all the way to quantum physics with photons and quarks in particle physics. Yeah, there's 3 exams at the end of the 2-year course. Paper 1 and Paper 2 both contain multiple choice and written questions. Paper 1's modules 1, 2, 3 and 5, and Paper 2's 1, 2, 4 and 6. Okay, and they're both worth 37%. And then finally Paper 3 just contains written questions, and it's on all the modules 1 to 6, and that's worth 26%. So, what is physics? Well, physics affects all things in life, and we use physics to create a model of the world around us. And that model can tell us about the release of energy during explosions. It can tell us about the structure of objects and buildings, and it can also tell us about the motion of particles. So all this is contained within physics, and the better our model is, the closer it is to the real world, the more we can use it and explain it. And that's what we're trying to do, create a really accurate model of the real world using our maths and equations. So we have equations such as this, which you might have learnt at GCSE. Acceleration equals change in velocity divided by time, and that's v minus u over t, and we have those units of acceleration, meters per second squared, and we can use these equations, the constant acceleration equations here. We can use these equations to describe the motion of objects. So the constant acceleration equations are ones you'll use on this course, and we would normally use them in this induction lesson to do a short experiment. Unfortunately, we can't do that today. Right, so what is this induction lesson mainly about? Well, it's going to be mainly about accuracy and precision. So these are kind of the foundations of physics, and that you'll rely on throughout the course when you're doing experiments and when you're handling the different numbers. Accuracy and precision, 2 things, they sound kind of very similar, but they actually mean some very different things when it comes to science. Accuracy is to do with how close you are to the true value. So if we were measuring a pencil, and there is a true value that pencil is, let's say it's 10.876 centimeters long or something like that. It's a true value, and accuracy is how close we can get to that true value. And then precision is all about the degree to which repeated values show the same results. So if we measured the pencil several times, how close those measurements get to each other is about our precision. And we can show this using an analogy of an archer. So an archer firing at a target, we can show here that in the first picture, if the center represents the true value, well, he hasn't hit the center at all, and all his results are different to each other. So he's got poor accuracy because he's off the true value, and he's also got poor precision because every time he takes a shot, it lands in a different place. The second picture shows poor accuracy because, again, it's nowhere near the true value, but there's good precision this time. Every time he takes a shot, he lands it in very close to the same place. So he's being very precise, even though he's getting an answer which is not the true value. And then finally, good accuracy and good precision should look like answers which hit the true value, but repeated results are also hitting close to the true value as well. So all the results are close together in the middle there. So accuracy and precision leads us to something called uncertainty. Whenever we take a measurement, we want to be able to convey to the person who's reading our results how certain we are of our measurements. So if I measure something with a ruler and I say it's 10 centimeters, someone could read that result and say, well, was it 10.4 centimeters? Was it 9.6 centimeters? And he's rounded up to 10. How certain is he of this result? And that's you can give a value for that. It's something called uncertainty. So that's how long is the pencil. We've done that. So uncertainty is a kind of a range of values we give to show between these two values the true value lies. So this is a very old object we have here. Give you a second to think about what that might be. Okay, it's actually this star, and it's one of the first stars born after the Big Bang. So it's a very old object. Now, astrophysicists have looked at the light from this star, and they calculated that this star is about 13.14 billion years old. Now, reading that, you could say, well, is it 13.14 billion and one, and they've rounded down or up, or how certain are they of that result? And they've given an uncertainty of 20 million years. So what they're saying is it's 13.14 billion plus or minus 20 million years. And that's their uncertainty. So they're certain that within those two values, plus and minus 20 million years, the true value lies somewhere. So that's an uncertainty, and we would call that an absolute uncertainty. And then there's also something called percentage uncertainty. So whenever you have a measuring instrument, you have an absolute uncertainty associated with it, and you can use that to calculate the percentage uncertainty. So here we have a voltmeter, and it reads 25.2 volts. Now we don't know what's going on inside the voltmeter, so we just have to assume the voltmeter is making a measurement accurate to 0.1 volts, because if it was plus 0.1 volts, it'd be 25.3, and if it's minus, it'd be 25.1, and it's reading 25.2, so somewhere between 25.1 and 25.3 is the true value which the voltmeter is reading as 25.2. Okay, so that's our absolute uncertainty. Yeah, so there it is. The finest division is our absolute uncertainty, 0.1. And to calculate the percentage uncertainty, we take that absolute uncertainty and we divide it by the reading that we've read off the meter. Okay, so it'll be 0.1 divided by 25.2. We times by 100 because we want a percentage. We get 0.4%. So the percentage uncertainty in this reading is 0.4%. What's the point of doing all that? Why don't you just use the absolute uncertainties? Well, in physics, we use values to calculate things. So the voltage that's been measured here might be used alongside the current to measure the resistance of something, calculate the resistance of something. So if you're not using an instrument that can directly measure the value you want to find out, if it's a calculated value you want, like resistance, and you're using voltage and current to find it, then you'll need to use several values to calculate your resistance. You need to use a value of voltage and a value of current. And each of those will have an uncertainty with them. And so why we use percentage uncertainties is because we can combine them. So you couldn't, for instance, you couldn't combine 0.1 volts with, say, plus or minus 1 amp, okay? But if you find the percentage uncertainty in both the voltmeter and the ammeter, you can combine them. And that's what we do here. So our formula in this instance would be for resistance. That's voltage over current. And so what is the formula doing? Well, it's doing A divided by B. And so it tells us here that we should add the percentage uncertainty of A with the percentage uncertainty of B. So our percentage uncertainty in A was 0.4%. Let's say the percentage uncertainty in B is 1%, and therefore adding those together gives you 1.4%, which is the percentage uncertainty in the calculated value of resistance in this case. So you can do this in lots of different ways. Whatever the formula says, you can combine the percentage uncertainties of the different values to give you the total percentage uncertainty in the calculated value. So this is where, at this point, we would do an experiment to get some values, and then we'd calculate the percentage uncertainty in that, and that would have been the induction lesson. But unfortunately, we can't do that. So instead, you're just going to have to use this example here and the combining percentage uncertainties to have a go at the exam questions which are part of the summer tasks. So what we'd like you to do to prepare for your start of your A-level here is there's 3 summer tasks to do. There's a research activity on PhET. There's a calculation sheet determining uncertainty, and it's got some worked examples for you, so don't worry if you kind of are a bit confused with that explanation. There's some worked examples for you to look at, and then 17 exam style questions, and we'll give out answers to these on the first lesson back after the summer. Thank you for listening, and I look forward to meeting you in September.